Thank you so much for having me this morning. It's always nice to come back to Mayo, and it's really nice to see so many familiar faces. So I'll be doing a quick overview of some of the work that my group has done over the past 7 years or so in computational pathology. Here are my disclosures. So we predominantly work on pathology images. It's often regarded as the last modality in cancer research to be digitized. It's a 150-year-old modality. It's been around for a really, really long time, but the computational analysis of these images is relatively very recent. So we see all these other modalities like genomics and proteomics and so forth that came about much later and they were inherently digital. So discovering from those kinds of data was digital to begin with, but the standard of care largely around the country and effectively around the world still remains looking at a glass slide under a microscope. So machine learning offers a really good opportunity to analyze some of this data. That's what we try to do, go from these images to everything in the red box here, whether it's early diagnosis, prognosis, prediction of response to treatment, but also we like to integrate other kinds of data when and where available to answer some of the interesting questions that we are trying to address. So I'm going to give an overview of some of our older work and then talk about some of the recent work that we have done. But looking at these images are very large. So from a machine learning point of view, the best way to solve the problem would be using multiple instance learning, splitting the very, very large image into smaller images, but that loses context. There are lots of issues around it. Back in 2021, we did a study where we brought in attention, so making it attention-based multiple instance learning together with instance level clustering to make it a little bit more data efficient using some of the inherent hierarchy that lies in these images. And there's a lot of redundancy in these images as well. There's lots of normal tissue, repeating patterns, making use of those to see if we can make the setup a little bit more data efficient while using just the labels that we have in a clinical setting, so without requiring any pixel level annotations, just using these images and the labels that reside in the pathology report. So this tool has been used quite a lot. It's been used in over 1,000 different studies and has been applied to all kinds of different disease models, downstream applications. So this is what the overall setup kind of looks like. We have a large image. We chop it into smaller patches. We can train it end to end, but that's how it was typically done. But we also can sort of extract features from these individual patches and then train a model on top of those features. In the beginning, we were just using a ResNet that was trained on ImageNet, using those features to see how well this can perform. More recently, this has been replaced by lots of self-supervised models, commonly now referred to as foundation models. And most of the work that you see in machine learning conferences either tries to improve the pre-trained feature extractor or some form of new aggregation. So this has become a relatively hot topic. You see a lot of work being done in all kinds of machine learning conferences. So this was applied to all kinds of different applications. Once we had this setup working really well, we try to target a lot of different applications, but here are a few interesting ones that were done in our group. We looked at cancers of unknown primary, trying to see if we can use just a weakly supervised multiple instance learning based model to predict what the origin of the tumor is. So I'm sure most people here are familiar with this problem, but for those who are not, when cancer metastasizes, it often becomes unclear where it may have originated. And the origin of the tumor, the primary site of origin, is really important because most treatments are based off of the origin. So we tried to pose this as being like an 18-class problem using lots of data from MGB, Johns Hopkins, and other institutions. This was back in 2021. We tried to see how well the model would perform. The model performed quite well. Since then, we have tried to expand this with a lot more data, and it's been deployed at MGH for several years now. And pathologists have an option to use it as like a laboratory developed test where they will get indications for what the top 3 possible origins might be. And then they can use those indications to order their ancillary tests, which is frequently done in this space to order, just confirm what the origin is by ordering those IHCs and so forth. More recently, we've tried to combine this together with molecular data using really fundamental data fusion paradigms just by concatenation to see can we improve outcomes by combining histology and genomics. And that's what we show here by combining histology and molecular data. So we made use of the Dana-Farber Brigham molecular profile cohort. It's about 22,000 patients with both histology and molecular molecular data to train the model, and was independently validated on lots of data that was sent from other institutions, really trying to see that can we improve like top 3, top 5 prediction of what the origin is, so you can effectively auto-order some of those ancillary tests before a pathologist is looking at it. So we're continuing to expand this to see can we include other kinds of modalities to improve origin prediction. Other applications that we use the same kind of weakly supervised paradigm for include endomyocardial biopsy assessment, trying to see if we can predict whether a donor heart is being rejected by the recipient after heart transplants. This is a common procedure, but it has a large amount of intra and intra-observer variability, and we thought that maybe you can reduce some of this intra and intra-observer variability by using machine learning in the loop, and that's what we did back in 2022 in this study. And there's a lot of analysis around what happens when you have human in the loop kind of assessment, when they look at these heat maps, how it changes and so forth in the article. Another aspect that we were very interested in, using the same kind of paradigms, can you combine histology and molecular data to improve prognostication? So we know that there are all these prognostic assays like Prosigna, Oncotype DX, and they can prognosticate the patient relatively well in some cases, not so well in other cases. But does the prognostication improve by combining histology and molecular data? That's what we tried to do in this study from back in 2022. It was run in a pan-cancer manner, trying to see if we can improve prognostication, but also answer some of these fundamental questions that is it possible for us to prognosticate patients just using histology alone, because histology is a much cheaper modality than molecular information, and might not be available in a lot of low resource kind of settings. But then you can also go back and look at what's important in the molecular profile and in the histology, because it's run in a more weakly supervised manner. So you have the entire histology image, or multitude of histology images corresponding that case, and the molecular profile. You're not, picking out some of these features and giving those features to the model. So the model picks out those features on its own. So it could be sort of a discovery mechanism, trying to figure out what it really uses. And we found a lot of interesting things, and we also put the entire database out there for people to discover from it. And people have found all kinds of very interesting correlations between features within the histology image and the molecular profile and outcome. And this paradigm has also been used for a lot of other disease models, including non-cancer, infectious, inflammatory stuff. This was from back in 2022. But looking at the overall pipeline, the most important component we found was the feature extraction component, and there's all this work being done in self-supervision. So we started to focus more on trying to train some of these self-supervised models. In 2022 there was in 2020 there was a New Reps article where we showed that you can make use of the hierarchy within the pathology image and train some of these models to improve feature representation at the level of the patch and at the level of the entire slide as well. And then last year we expanded this into 2 self-supervised models focused on pathology only, just the pathology image, and also contrasting with text to improve image representation. And really the goal here was to develop these self-supervised models as feature extractors. I know there's a lot of people are thinking of these foundation models as some kind of oracles that they would solve all problems in pathology all at once. That's really not the case. They're really just feature extractors that you can use in like a multiple instance based setting or some other setting. But people also use them for zero-shot, few-shot settings, and in those cases they're often meant to be used just to see how rich the feature representations are, and they're not at a level where they might be used for clinical purposes. But as feature extractors, they work relatively well and do much better than what the standard was before, just using a ResNet trained on ImageNet. So we made these available, and they've been downloaded over 1.4 million times over Hugging Face, and have already been used in over 600 different studies, basically applied to every major organ system, which was very exciting to see how what kind of impact these models have had. And the performance on at least image-based models has begun to saturate. There's a lot more foundation models out there now since we developed some of these initial models, and it's very interesting to see how the performance has saturated, at least for image-only models. So similar to what's been happening in the machine learning community, by contrasting with text or other kinds of modalities, we can improve representation for each one of these individual modalities. So that's what we also did in this other study, where we contrasted with text. So I'll talk a little bit about this really quickly. So for the image-only study, we used about 100,000 whole slide images, and the way we went about doing this is that Meta showed in their DynoV2 article that the diversity of the data is way more important than the quantity of the data. So we went and looked at our entire archive at MGH and the Brigham, and picked out the most diverse cases and used those diverse cases for this initial training. More recently, we've also expanded this into what we call UNI2, which uses about 350,000 cases. Another thing we found was that using basically data in the entire department in a more exhaustive way, using all of oncology data, but also all of infectious and inflammatory disease data, drastically improved performance across all downstream tasks that we were evaluating at the time. So initially we assessed this on 33 different downstream tasks. Some have more clinical relevance than others. Some tasks were just posed to see how rich the feature representation is, because we really wanted to push the limit as to how far we can go. So we also focused on tasks like, can we classify all of the OncoTree codes within the OncoTree system using pathology images. Since then, we've expanded this substantially to include a lot more data in pre-training, but also the downstream assessment. We have much better tasks for it, both at the level of the slide as well as in a few-shot setting. And few-shot is very exciting in pathology because you don't really have a lot of cases for rare disease, clinical trials, and all these other interesting situations that exist in pathology. And then at the same time, we also looked at, you have corresponding text. So we used 1.1 million pathology images in the PubMed Open Access database and tried to see, can you contrast with those with the corresponding text captions to improve image representation. So that's what the study sort of focused on, and we showed that you could do that and drastically improve performance on, in particular in a few-shot setting, which has been quite good. There has been sort of other applications of this because we were using a lot of PubMed data. We could only use a small subset of the PubMed data that had like an open access license, but we still use data from PubMed. And because it was very diverse, the CONCH model continues to have a lot of utility because of the diversity of data. It has a lot of downstream applications where it applies even to non-pathology images. So it's been interesting to see how people have been using it with forensics, plant pathology, and all kinds of other applications as well. So once we had these kind of models working at our region within the slide, the obvious next step was that, can we scale this to the entire slide? So we started by looking at very fundamental methods. Can we just use really a mixture of experts, other kinds of really fundamental methods to see, can we build a slide level representation of the entire model. So that's how we started, by looking at this. But more recently, we've expanded this into a much larger study where we used all of the data that we had available, but had 3-stage training. So we used a number of different what we had learned from the Pastel models, but also some other tips and tricks that were being used by the large language model community, like training short and testing long. So training on a smaller region within the slide, and then testing on a much larger region. So this was 3-stage training. So the first stage was just an iBot model, so that's the self-supervised component, and then you can contrast with the pathology report, but the pathology report is obviously limited. It often does not have detailed morphologic description, at least not at major cancer centers. If you look at reports that come from more community medical centers, they have a much more detailed morphologic description. So we also use a generative model to generate some of those morphologic descriptions that I'll talk about in a second. And as our models are getting better, we're also trying to improve our benchmarks. So we had several of these benchmarks that were really, the goal was not to get to clinical utility, but to see how difficult of a benchmark can we make where the model would begin to fail, right? So really difficult benchmarks like classifying multiple cancer types, but also looking at pan rare disease classification in hundreds of classes in a singular model, and comparing how well this model would do in comparison to some of the other models. That's what we try to do, and then also assessing whether multimodal contrasting helps in this particular case. So we also assess this in a few shot setting, as well as trying to do retrieval and search and finding similar cases in a rare disease kind of a setting as well. So we contrasted with text and found that contrasting with text improves representation for the image, but there's a lot of other additional data in pathology that you could be contrasting with to improve representation, right? Like corresponding special stains, IHCs, molecular data. So that's what we tried to target next. So in this ECCV article from last year, we contrasted with IHCs and special stains and tried to see, can we improve representation for both the image and those IHCs, and we showed that was possible, applying it to downstream applications like survival, outcome prediction, and for IHC scoring itself. And then this CVPR article from 2024, we tried to see, can you contrast with transcriptomics? So initially this was done on sort of a toy example, just by using the TCGA. Contrasting with transcriptomics helped improve representation quite a lot, and that kind of makes sense because we were contrasting with text, which is more subjective, whereas transcriptomics is a much more objective second view of the same case. So we were able to improve representation quite a lot, where few shot performance drastically shot up for some of these difficult tasks, including for we looked at breast cancer and lung cancer subtyping, but also toxicology assessment in rodents. So this was the first indication that we should really scale this idea of contrasting with molecular data. So that's what we did next. So we contrasted with all the data that was available to us at Brigham and MGH, all the molecular data. So this includes the large NGS assay that runs at the Dana-Farber Brigham Cancer Center, but also the transcriptomic assay that runs at MGH. So because we're contrasting against across modalities and not necessarily fusing them, we can have multiple different forms of molecular data all used to improve image representation. So that's what we try to do here, and then applied it to all kinds of different downstream tasks, and in particular found that the more challenging tasks like treatment response prediction did quite well in this case. This is an example for treatment response prediction. Treatment response prediction from histology is a difficult task to begin with because you don't always have a lot of data available, a lot of pre-treatment biopsies available, and it's also very difficult to get clean labels for this. So there's just limited data available in this setting, and it's a difficult task morphologically as well, just predicting treatment response from the histology images. In certain cases it could be easy, but these are some of the more difficult cases where we found that by using about 50,000 cases contrasted with histology in a pre-training setting, when you post-train it with this data, it works relatively well. So we have all these, self-supervised models, contrastive models, with the goal of improving pre-training and improving representation. But an obvious next step for us was to see if we can build like a multimodal large language model that would try to cater to all of human pathology. And why we believe this to be the case? Well, companies like OpenAI are trying to build singular multimodal large language models that would cater to all of human knowledge. We know these models are, very high capacity, and human pathology knowledge is a very small subset of that knowledge. So we should technically be able to build a model like that if we have enough instruction data available. So it's all about the instruction data. So we started focusing on curating large amounts of instruction data manually, and quickly learned that this would be very difficult to do across all infectious, inflammatory, and neoplastic disease. But being at Harvard teaching hospitals, we have a large resource of all the teaching and training materials that are used for residents, for training residents, across all of our hospitals. So we gathered all of those materials and converted them into instructions for this model. So we try to train it from scratch, as well as from pre-training, from Quen models, other kinds of language models, to see what would work better. And then eventually the goal was to have a generative model where we can start asking questions from the pathology image. In the beginning, we managed to get an instruction set of about 500,000 images, questions, and answers, but more recently we have scaled it to about 5 million. So we have a drastically large instruction set, which to our knowledge includes every known entity in human pathology, including infectious, inflammatory, and neoplastic disease, including some very rare diseases that we have sourced from over 100 institutions across the country. So it can, in the beginning, it was sort of answering these very fundamental questions. We did a lot of assessment, looking at how well this would do in comparison to some of the more generic models like GPT-4V and more recently GPT-4o, but also assessing it against pathologists and how well the model performs when we ask pathologists to compare the performance across models. And we found that the model does very well in morphologic descriptions as well as for making diagnoses. But how do we use this in a more of a clinical setting? So we've been thinking about this quite a lot. So there's been a lot of scalability of this model. So this model was licensed to a startup, and they have really scaled it and have tried to assess that where can it be a very good efficiency tool in the entire pathology process. This is just an example for what they have effectively done. So for every pathology case, there can be lots of positive slides, lots of negative slides. So you can use PathChat to separate out all of the negative slides across infectious, inflammatory, and neoplastic disease. So it will screen all those slides and separate them out. Then if the pathologist wants any assistance, they could ask PathChat any question at any level of abstraction. So you can ask a question at the level of the region, at the level of the slide, or at the level of the entire case. Another really good use case of this is that you can look at the PathChat can look at the initial set of H&E slides and order any additional tests that would need to be ordered by the time the pathologist is looking at the case. Those tests could be already ordered, and they could be assessing those slides in one go, rather than having a time lapse between when they look at the slide and when the tests are ordered. And finally, you can also write the synoptic report for you. So effectively looking at where can generative AI help across the entire pathology spectrum, and then PathChat as a good morphologic descriptor that can understand these images come in and help. Eventually, we will have much more use, combining this together with agents and all of that. But this is where it is. It is at this point. We've also looked at building foundation models for other modalities like proteomics. This is some work that we did together with Shizun Jiang's lab at Harvard, where we have taken large amounts of pathology data, large amounts of proteomics data, and have built models that would represent proteomics data into what's now often referred to as virtual tissues, but I'll just continue to call it an embedding or a representation. And then I've applied it to all kinds of different downstream tasks, including for patient stratification, but also for a lot of the pre-processing that goes into this data. So we have all these models publicly available, and there's a large community that has already started to use this proteomics model as well. So I will talk a little bit about AI agents before closing. So I think that computational biology in general is really ripe for automation through AI agents, because in its most fundamental form, what we're often doing in computational biology is bringing new kinds of data to existing tools. Of course, we build all kinds of new tools as well, but this is the most common thing that we're often working on. And the situation is, the current technology is like really ripe to take instructions and go and execute, using new data, making use of all those tools, right? So the goal is to go from a set of from a human prompt to a set of instructions that the model can then go execute together with all of these tools. So that's what we have tried to build in this particular setting, and we are doing it for pathology because that's what we predominantly work on. But the framework is more generic, and more recently there have been all these search tools, language tools that we have really made use of to enable this. So it's just a quick example of this. So in this case, the user is saying that, well, here's my data, and this data is corresponding a set of responders and non-responders. Can you go train a model where we can assess whether there's any difference between the responding and non-responding cohort, and then it makes a plan and goes and executes that plan. In this case, it's pathology images. So we'll segment the tissue, extract the features, and train the model, and then go assess what the model would do. This is very simplistic to build, surprisingly, but very, very powerful in the sense that it can lower the barrier for who could be doing this kind of research on this data. So before we had tools like this, a pathologist, for example, who has a good idea for a computational pathology project needs to come to our group or some other group that predominantly works in this area. With this kind of agentic tool, you could just go build it yourself. So it says that here's the AUC. You might ask that what regions the model is using to make some of those determinations, and it can go in and look look at some of those regions, but that's like more like reading the tea leaves to get a more deterministic answer for what the model actually used. Maybe you want to look at everything in your test set and see what's common across the high attention regions within all of those images, and then use a generative model to explain it in text. So that's what we do. So we invoke PathChat to explain what's in all of those high attention regions. This is just one example for treatment response. We have given it to about 100 different researchers, and they've used it for all kinds of different applications. So really, the power is in trying to democratize some of this very fundamental analysis that you needed to run in code, that now you can run through like a simple GUI. We've also been very interested in 3D pathology. So human pathology today is two-dimensional, but tissue is three-dimensional. So we often miss a lot of stuff. There's been over a dozen studies showing that if you cut additional sections from blocks, the diagnosis kind of changes. And there's all this work in trying to image tissue in 3D. There's limited computational frameworks. 3D volumes of tissue can be difficult to analyze. But also it's more difficult to discover from these like very massive pathology images that are large to begin with. If you add another dimension, they become very, very large. So in this study from last year, we tried to see if we can scale this kind of multiple distance learning paradigm in 3 dimensions. It became obviously very, very computationally complex, but we managed to do it. And we also managed to make all of these tools publicly available. So it's very exciting to see how people have been using it for all kinds of other applications. So this study focused on prostate cancer, but people have used it on other non-cancer, pre-cancer kind of applications as well. And then once you have these models trained, you can look at how separable the patients are when you use the entire 3D volume rather than just using a 2D section or a multitude of 2D sections alone, whether that 3D morphology actually helps and benefits this, right? So this is a large part of this. And then you can, of course, look at the 3-dimensional heat maps. So before I close, I'm just going to say a little bit about what we're working on next. So we learned a lot from building some of those foundation models in pathology and how they can act as pre-trained models for other kinds of downstream models that can be built on top of them. And we're trying to expand this to all of the data that we have available at MGB. So we have collectively have around 10.1 million patients at Brigham and MGH, and we have sort of cleaned up, de-identified all of this data across the two hospitals, including everything that we have in the digital record. And the goal really is that can we build a foundation model from all of this data such that you can represent the data into a single representation at any given time point. So at any given time we can have self-supervised models that represent these individual modalities and then aggregate them into a patient level representation that is also temporally aligned, right? So with every new visit, every phone call, every new information that becomes available about the patient, the embedding can then update, and we can have this temporal trajectory of the patient, how it moves within feature space. And then you can apply this to all kinds of downstream applications, including early diagnosis, prognosis, and prediction of response to treatment. So we have a first version of this model that we are trying to assess internally, including data from other Harvard hospitals and other hospitals in our community, and we'll soon be using data from other hospitals outside the country as well to see how well the model works in some of these very interesting tasks, but also working with pharma to see if we can do clinical trial matching. So the next few months would be very, very interesting, and we'll have more to say about this towards the end of the year. I'll stop here in the interest of time, and I'll thank all the PhD students, postdocs who have contributed to this work and all the funding that we have received. Thank you.